Alright, in this video we're going to look at Unit 3, Objective 6, Integration by Parts. So we're going to start by kind of looking at something we've seen before, an antiderivative x cosine x. So if we're looking at this, clearly we don't have just a plain rule for x cosine x. If it were just x, or if it were just cosine x, we'd be alright. So we got to think u. Well, usually our u is inside parentheses, and we can kind of think of this thing as x times cosine of x. So our first thought might be u equals x. So then du is going to be equal to dx. But we have a problem, because I have an x dx in my problem. And if we make this substitution, really we're just turning this into the antiderivative of u cosine u du. And that really doesn't help anything. So that's probably not what we want to start with. So then our other option would be, how about we take all of cosine? Well, then du is going to be negative sine of x, and that's a whole nother set of problems. So that doesn't work. So it's looking like there's nothing we can really do with our u substitution. So when that happens, we have to use something called integration by parts. So when we antidifferentiate, or when we need to antidifferentiate a product, but u substitution doesn't work, antidifferentiation by parts. So how, or what this looks like is we're going to say that the antiderivative of u dv is equal to u times v minus the antiderivative of v du. And there's a product rule proof behind this where the uv minus v du comes from, but we're not going to get into it in this video. If you want to look it up, it's on page 341 in your textbook. Now, this whole thing, instead of just picking a u, we're going to need to pick a u and a dv. So the key to doing this correctly is making sure we pick the correct u. So to make sure this, or to pick this, we want to use the mnemonic lipet, L-I-P-E-T. In this order, these are how we want to pick our u's. So the first thing we're going to look for, the L, stands for logs. If there is a log in your problem, that's your u. If there's no logs, we look for I, which is inverse trig. If there's no inverse trig, we move on to P, which is polynomials. And if there's no polynomials, we move to E, which is exponentials. So stuff like e to the power of something. And finally, if there's no logs, inverse trig, polynomials, or exponentials, we look for just regular trig functions. Now, the one that's going to happen most is going to be our polynomials, and don't forget things like x or 3x are polynomials. So it doesn't have to have multiple terms, just something like x is a polynomial. So let's revisit that first example that we started with, x cosine x. So we know our u substitution doesn't work, so we think about integration by parts. So we need to think, what is our u? Do we have any natural logs? Any logs at all? No. No inverse trig, but we do have a polynomial. Our polynomial is x. So we know u equals x, so that means dv, right? We're going to have to pick a u and a dv. dv is going to be everything that's left over. So cosine x dx is our dv. So we have u, we have dv. What we need, if we look back at our rule, is we also need a du. So we're going to take that the same way we did a second ago, or in the previous section. So u's derivative is du, x's derivative is dx. But we also need a v. So if we start with dv, and I want a v, well, that's starting with the derivative of v. I want just plain old v, so we have to take the antiderivative. The antiderivative of cosine is going to be sine of x. So, again, we start with our u and our dv. We differentiate to find du, and we antidifferentiate to find v. Now we have u, v, and du. So looking at our rule, we know that the antiderivative of x cosine of x dx is going to be equal to u times v, so x sine of x, minus the antiderivative of v du, so sine of x dx. Now we still need to actually take this antiderivative, so our antiderivative of sine of x is going to be negative cosine of x. And we have a plus c, two negatives are going to give us a positive. So the antiderivative of x cosine x is going to be x sine of x plus cosine of x plus c. And if you wanted to check your answer, you could take the derivative. Just make sure you use your product rule here, and you should end up at x cosine of x. Let's look at another example, some things that might happen. So if we're looking here, we have x squared e to the x. So if you were thinking real quick about just plain old u substitution, our first thought would be x, because that's our exponent of e. Derivative of x is just 1 dx. That doesn't help us with the x squared. If we make x squared our u, we have a 2x. That doesn't take care of the e to the x. So we have to think about integration by parts. So think about our u. We don't have any natural logs. We don't have any inverse trig. We do have a polynomial. The polynomial is x squared. So u is x squared. dv is everything else, so that's e to the x dx. du is 2x dx. v, the antiderivative of e to the x, is just e to the x. So we can look at this and now say the antiderivative of x squared e to the x dx is going to be equal to uv, so x squared e to the x, minus v du, so 2x e to the x dx. I'm going to pull this 2 out front. Alright, so now we have to think about this antiderivative here. So we think about it, we might need a u, because this isn't just a rule that we have. So u might be x, then we take its derivative, get du is equal to dx. We have that x left over. If we make this our u, and then it doesn't get rid of the e, so we're back where we started. We need to think about anti-differentiation by parts again. So twice in the same problem. So again, there's no natural logs, there's no inverse trig. We have a polynomial that's x, so u is x, dv is going to be e to the x dx. du equals dx, v equals e to the x. So this piece here becomes 2 times uv, so x e to the x, minus the antiderivative of v du, e to the x dx. And the 2 just came from the 2 outside of our antiderivative. Looking at this, we can do this one pretty easily. The antiderivative of e to the x is just e to the x. And we also have, don't forget, this stuff up here. So moving everything over this way, our answer is going to be x squared e to the x minus 2 times the quantity x e to the x minus e to the x plus c. And if you wanted to simplify a bit, you could. You can distribute your 2. You can factor out an e to the x from everything, but we'll just kind of leave it here for now. So this is one of those weird problems where every so often we're going to have to use anti-differentiation by parts more than once. We're going to get to this integral and we're stuck again. So if that happens, there's a thing called tabular integration. So if you have integration by parts problem that you can see is going to take more than one integral to complete, you might be able to use tabular integration. In order for this to happen, though, two conditions need to be met in order for tabular integration to work. The first condition that needs to be met are u eventually needs to differentiate to 0. our dv needs to be easily anti-differentiated many times. If those two things happen, we can use our tabular integration. So how this works. So we're going to start with, we're going to start with the same problem we just did. The x squared e to the x. And we know from doing this earlier that u is going to be x squared, dv is going to be e to the x. Now how tabular works is we want to make two columns. The first column we want it to be u and derivatives. And the second column we want to be dv and antiderivatives. So we start out with u being x squared and dv being e to the x. This is eventually going to differentiate to 0, right? We take a derivative 2x, take a derivative 2, take a derivative 0. Oops. Now we want to take antiderivatives. Well, antiderivative of e to the x is just e to the x, so we could do that forever. So once you hit 0 with your derivative, that's how many antiderivatives you're going to want to take. Now how this works is we want to take this first term, multiply it by that second term. We want to take this second term, multiply it by that third term. This third term, multiply it by the last term. Then we want to alternate between positives and negatives. So x squared e to the x, negative 2x e to the x, positive 2e to the x. And if you went through with the simplification on the last problem where we would distribute the 2, you would end up here. Now we also need a plus c because it's an antiderivative. So that's a quick way to do anti-differentiation by parts if it's going to take more than one go. Again, in order to do that, it has to u has to differentiate to 0, and dv has to be easily anti-differentiated many times. So we'll call it quits on this video, and we'll see you in the next one.